this. Okay, so that is how you can compute the angle bisectors using the Stewart relation, relation of Stewart. Actually, very much the same reasoning can be used to compute the length of the external angle bisectors. Let me clarify the issue. Okay, so you see just as, okay, so let me complete this picture perhaps. In a triangle, you can have the angle bisector dividing the angle internally into two parts, and you have got another line which is perpendicular to it, which divides this very same angle externally. And okay, so it intersects the opposite side in some point, let's call it JA prime, and its length can be designated as NA prime. So much the same, very much the same reasoning can be applied. And you can find P's and Q's, etc., for the external bisector and apply the Stewart relation to obtain the following formula. This, I'm not going to do it, I'll leave it to you. There are one or two peculiarities. For the external angle bisector. So that's the internal angle bisector. That is the external angle bisector. The formula is a little different. Well, that's, as you can see, I cannot remember it myself. It is 2 divided by not b plus c, but b minus c. I'm making a deliberate mistake. Square root. Well, instead of s minus a, this time you have got s minus b, s minus c, and bc. Okay, so rather formula is closely related, and the deliberate mistake which I have made is, of course, that b and c, I don't know which one is larger, so this quantity can turn out to be negative unless I take the absolute value, of course. So you have to take the absolute value. And there is, of course, one interesting feature of this formula. You see, when b minus c becomes small or eventually 0, the external angle bisector becomes large, or if I may allow to utter the I word, it may become infinite. Okay, so, well, that's rather obvious, isn't it? I mean, if you've got an equilateral triangle like this, then the external angle bisector will actually never intersect the opposite side. So for practice, so that's the situation when b is equal to c, so that the denominator will be 0. Of course, so I have to make clear that this formula works for b is not c. So it does not work for an isosceles triangle. It works only for non-isosceles triangles. So this is left to the student. Actually, you can look it up in my lecture notes. Okay, now I would like to talk now a little bit about a problem which has become the nightmare of the mathematical world in its time. It's a so-called Steiner-Lehmus problem, or Steiner-Lehmus theorem nowadays. Steiner is one of my great heroes, a great geometer, I think, early 19th century, I'm sorry. Well, I'm sorry, I shall provide information about Steiner too, so please have some patience. Okay, apparently a person, not a famous person, I really don't know, possibly an amateur mathematician, wrote Steiner, or some other member of the mathematical community in those days, and asked a very simple question. It's the following. It's nowadays called the Steiner-Lehmus. Hanımlar beyler, ladies and gentlemen, this name Lehmus, nobody knows anything about it. And he's apparently completely forgotten except for this one small result. The Steiner-Lehmus theorem, or problem, let's say. It says the following. If you've got, of course, if B is equal to C, so if your triangle is an isosceles triangle, then clearly NB is equal to NC. So if your triangle is an isosceles triangle, so if you've got something like this, okay? So these two sides are equal, these two angles are equal, A, B, C. If you've got a triangle like this, then the internal bisectors, okay, so let me use a little color. So the internal bisectors are equal in length. They are, in fact, they are congruent quantities. So they are congruent shapes. Okay, so something like this, I don't know. Okay? So that's your N C, and that's your N B. Okay? So if it's isosceles, then your triangle is, in fact, your triangle has equal internal angle bisectors. The problem of Lehmus was the following. Is it true that in a triangle in which two angle bisectors are equal, does it follow that the triangle is isosceles? Okay, so here's the thing. Okay, so let me redraw this thing. So let's not think about this. Let us take a triangle quite generally, okay, and let us assume that it's being given to us that the internal bisector at B and the internal bisector at C are equal in length. So that is your NC, and that's your NB. If NB is equal to NC, does it follow that B is equal to C? This problem, hanımlar beyler, looks very innocuous. I mean, it seems to amount to nothing. Indeed, very innocuous. But you see, for instance, do you remember in my very first lecture, I told you the following. If the two altitudes, HB and HC, are equal, then you must have B is equal to C. This is very simple. You'll just look at the area formula. On the other hand, if MB is equal to MC, we know that B is equal to C. I did this too. So in fact, these implications are both-sided, and this implication in this direction is trivial. So in view of these facts, you would rather expect that in a triangle in which the internal angle bisectors at B and C are equal in length, that triangle must be isosceles. B and C must be equal. Well, it turned out that the problem was terribly hard. You can't solve it by elementary means. In fact, it remained unsolved for a very long time until Steiner attacked the problem. And I'm not quite sure. I used to know the history quite well. Steiner actually solved the problem in a very general case. And I don't know exactly Steiner's solution, but I know a version of it, but I don't care. But you see, when you have this formula, then you can actually solve the Steiner-Lehmus theorem. So it is in fact the kind of solution which I think would very much appeal to to this psychology of the students. You see, I think you love that kind of thing, don't you? Okay, so solution. Let's start with this. Let's start. And let's use this formula. So what is NB? Check that, of course, this formula is for NA, but we can write it for NB. How? Well, NB is, of course, 2 divided by C plus A, square root of S minus B, C, A. So I have moved everything cyclically. Equals, and C. 2, I move everything cyclically, A plus B, square root of S minus C, A, B. Well, immediately, of course, you can strike out the 2's, S's, and A's. Go on. Okay, so you know the rest. Take the square. Okay, you've got an inequality, and I think you love this kind of manipulation. And actually, I'm not going to do that. I'm not going to do that. Do it because you see, I may ask it I may set it as an exam question. So you go on like this, and you will end up with B equals C somewhere along the line. Okay, that's a terribly ugly proof. That's a terribly ugly proof. Well, to be quite frank, there are no pretty proofs of Steiner-Lehmus theorem. So this is among them. Okay, so you can actually solve the Steiner-Lehmus theorem once you can use the Stewart relation to compute the internal angle bisector. Now here comes yet another surprising thing. Okay, the final surprise, let's say. Let's say the final surprise. Okay, so now that we have found successfully also a formula, in fact a very similar formula for the external bisector. And I think, Lehmus was a pretty insignificant person. Nobody knows anything about him, but he could immortalize his name by asking a question which turned out to be terribly difficult. In fact, it could be solved by Steiner himself, possibly the greatest geometry person at that time. So why not ask a similar question? Let us ask ourselves the following question. Is it true that if the external bisectors turn out to be, if the external bisectors are equal, can I conclude from this? Can I conclude from this that the triangle is itself equal? The triangle itself is isosceles. The surprising answer to this question, Çocuklar, is this is not true. Not true. Not true. And in fact, it is possible, not true. I shall leave it to you. I shall leave it to you to construct a thing. So I will give you a triangle. I will give you a triangle which was discovered by Bothema. Bothema is, I think, a Dutch. I'm not quite sure. Bothema is apparently geometer, Dutch geometer, I think. Okay, I shall provide the details. Never mind. Okay, it's nowadays referred to as the Bothema triangle, and the Bothema triangle well, the Bothema triangle is the triangle in which here we are. Angle A is 36 degrees. And B is 12 degrees. And C is, well, what remains? 132 degrees. If you take this triangle, çocuklar, you will find that in this triangle, in the Bottema triangle, show that. So I leave it to you. This is left to the student. In fact, you can check it up in my lecture notes. Left to the student. You can check the following. Show that. In fact, obviously, I mean, look at these triangles. Obviously, the triangle is not isosceles. Değil mi? İkizkenar değil, it's not isosceles, obviously. But you can prove that, you can show that NB prime, so the external angle bisector at B, is equal to NC prime, and in fact, it's the length of BC in this triangle. So that's a very curious. So it's a very thin triangle, you know. It is something like this. It's very thin. Okay, so very thin like this. That's 12 degrees, huh? And then that's the angle at B, and you've got A, and that's you have got 36 degrees like this. Okay, and that's C. Okay, so something rather like this. Okay, so that's A, and in fact, if you now construct the external bisectors, they will look rather like this. So, for instance, okay, so yeah, okay, so they will look rather like this. Okay, so it will, for instance, something like this. I don't get it quite right. Okay, so this will be NB prime, and this NB prime and BC will be equal, and NC will be something like this. I'll leave it to you to check. So that's NC prime. So you will have something like this. So that's the external bisector at B. That is the external bisector at C, and that is the side. All these three, 1, 2, 3 lengths will be equal. If you get here 132 degrees, 12 degrees, 36 degrees. This was discovered by Bottema. You know, it's a surprising thing to happen. Surprising thing to happen. You know, well, I think a rather lovely situation. Okay. By the way, in my lecture notes there is a proof of Steiner-Lehmus theorem. It's not a very pretty proof by myself and Hüseyin Demir. And you know, there are lots and lots of proofs nowadays, but as the final surprise shows, it doesn't work for external bisectors. Well, there it is. Okay, so these are some applications of the Stewart relation, I mean the cosine rule and the Stewart relation, so on and so forth. And I think we have got just enough time to give you a yes. Exactly. Okay, so I can now erase the left-hand side of the blackboard. Now I would like to give you one final, so that's the fourth application, I think, of the cosine rule. This is yet another elementary problem of the 20th century, and another problem, just like Morley's problem, which baffled the mathematical community because it was an elementary question, yet it could not be solved by many professional mathematicians for 20, 30 years, I think. I'm not quite sure about history. It is a problem which has been proposed by the Hungarian, you know, mathematician of Jewish extraction, Erdős, Paul Erdős. Paul Erdős, I mean, you must have heard about him. You know, he is such an iconic figure in the world of mathematics. So died very recently, Erdős. And this problem was proposed by Erdős and solved much later by Erdős-Mordell. So that's my fourth application. Number 4. This is the Erdős-Mordell theorem. So it was proposed by Erdős, yet solved by Mordell. So Erdős-Mordell inequality. Now this time I shall actually write down the inequality and then proceed to prove it. Well, the inequality is the following. Yes. In any triangle, take any triangle. And ABC, and take any point inside it. Actually, the problem can be reformulated for any kind of point, not inside, but maybe possibly outside, but that's too much work. Let's take any point, P, okay, inside the triangle, and let's assume that the distances to 3 sides are given, and they are called, let's call them R1. The distance of P to A is R1. Distance of P to B is R2, big R2. And again, uppercase R3 designates the distance between P and C. Okay, and let's now look at the distance of the point P to the 3 sides. That means you drop perpendiculars to each side and you measure the length. Well, let this be small r1. Drop perpendicular, small r2. Drop perpendicular, small r3. Okay, here is the inequality proposed by Erdős, that the sum of the uppercase r's, r1 plus r2 plus r3 is in fact larger than twice the sum of the distances to the sides, small r1, small r2, r3, and this inequality in fact turns into an equality if and only if ABC is equilateral and P is its center. Check that. You will now raise your brows and say, Professor TEZER, which center? Is it orthocenter? Is it circumcenter? Is it the centroid? Which kind of center? It doesn't matter. They all coincide, you know. It's in an equilateral triangle. They all coincide. That's why you drive me crazy when I ask you to draw a triangle and you give me an equilateral triangle, okay? So when you draw an equilateral triangle, it means that right at the beginning you have lost all valuable information. So don't do that, okay? I'll resent that, okay? Right, so if the thing is equilateral and P is its center, then this becomes an equality. Does it really? Let's have a look. This is an equilateral triangle. It doesn't matter what the side length is, let's say A. So if you have got the center, then this length, okay, so what's the height? The altitude is, of course, this, isn't it? And so this part, so it means that R1 is 2 over 3, square root of 3 over 2, A, and small r1 is in fact 1 over 3. And of course this is r2, this is r3, and this is small r1, this is 2, small r3. Okay? Well, if you take 3 times this object, it will be of course twice 3 times this object. That's rather nice. Yeah. Okay. So how do I prove? Okay. So that's the Erdős-Mordell inequality. I would like to give. Okay. So this, as I said, has baffled the mathematical community for a very long time. But now there are numerous proofs, and one of them, which I think is due to Kazarinov, a person who is rather famous with inequalities of geometric origin. Okay, so anyhow, I don't know. I will provide historical details later. Okay, so may I make a small interlude, brief interlude, to talk to you about, very brief interlude. Of course, you know that if I give you 2 positive quantities, then the arithmetic mean will be larger than the geometric mean, and they will be the same, arithmetic mean will be the same as the geometric mean if and only if these 2 quantities are the same. Hatırlayın. So you've got this, don't you? Okay, why is this true? Do you know the proof? Well, of course. I mean, if you take square root of x minus square root of y, and if you square it, then this is positive, isn't it? And when does this become an equality? If x is equal to y, right? So let's do this. This is x plus y minus 2 times square root of xy. That's larger than 0. They are the same. Okay? So that's the fastest proof. That's the fastest proof. Well, I would like to also point out another thing, since you know this. Şuna bir bakar mısınız çocuklar? I would like you to look at the following thing. If you take any x, y positive, and if you write x over y and y over x, now this must be strictly larger. This must be larger than 2. Why is that? Yeah, you know, the sum of 2 things is larger than their product square rooted. X over y, y over x. The sum is less than the product. What's the product? If you take the product of these things, x cancels x, y cancels y, so you've got only y. 1, square root of 1 is 1. Take it twice, that's it. And when does this become an equality? Well, they become an equality only if these 2 quantities are the same. So only if x is equal to y, right? Okay, so you remembered them. Okay, so very trivial. Now you go on. Okay, right. Now I would like to look at this part. Okay, so what's happening near the vertex A? So if you wish, let me give names to the feet of the verticals, respective feet of the verticals on BC, on CA, on AB. Okay. Okay, so KLM. So let's look more carefully at what's happening near A. Okay, so it is something like this, isn't it? So let me draw a larger picture. So that's my P. That's A. So that is R1, which is fine. And that is, that's my L. That's my M. I'm dropping perpendiculars on the 2 sides. Okay, so and of course this is length small r2. This is length small r3. Now let me write down something rather simple. I don't know. Perhaps, yeah. I will, of course, use the sine rule now first. The sine rule. So, in fact, in this inequality, in the proof of this inequality, I'm using the sine rule as well as the cosine rule. But the use of the sine rule is rather fleeting. The sine rule in the triangle AML. In the triangle AML, so that's something like this. If you put a circle through ALM, it will also pass through R, and of course, okay, and of course, the line segment AP will be a diameter because you see these angles are 90 degrees. So this is in fact twice the radius, twice the circumradius in the triangle AML. So the sine rule tells me quite simply that R1 is equal to, if you like, I can write it like this: R1 times, R1 times sine A is in fact equal to the length LM. Okay, so I would much rather write this like this: R1 is equal to LM divided by sine A. Let me start with this. I would like to start with this. Şimdi, about LM, I can say the following. About LM, I can say the following. That now, okay, so how do I compute LM? Now I shall use, now I know that this is small r2, this is small r3, and this angle is A, and this angle, of course, is the angle that complements A. That's of course pi minus A. So I can actually, in this triangle, apply the cosine rule. So I apply the cosine rule to find LM. Well, it is of course R2 squared plus R3 squared minus 2R2 R3 cosine pi minus A. So instead I write this cosine A. Well, this quantity has to be square rooted, of course, and divided by sine A. How did I obtain this? Well, this is the cosine rule. The cosine rule in the triangle not AML but PLM. Okay, so that's an interesting relation between R1 and R2, R3, which is rather nice. Şimdi bakın. Instead of, okay, so some tricks. I'm sorry about that. So R1 is equal to. Now I shall replace A. So I know that A plus B plus C will make up to pi. So instead of A, I shall take pi minus B minus C. So this will change sign again. So I shall have R2 squared plus R3 squared. Now minus 2R2 R3 cosine B plus C. Okay, so of course I've got this whole thing square rooted, and downstairs once again I'm carrying around that sine A. Okay, now, right, here comes a trick. Perhaps I should take one more step before I give you the trick. So let me write this down. I would like to write this again. So I've got sufficient time, I do hope, because this will take some. No, okay, I've got sufficient time. Okay, so R1. Okay, so I've got R2 squared, fine. R3 squared, fine. And now I can write this as minus 2R2 R3. Well, instead of cosine B, I write cosine B plus C, cosine B, cosine C. Okay? And then I've got exactly the same sort of thing, of course, with the opposite sign, 2R2 R3 sine B. sine C. Okay, so all this is of course within the square root sign, which is rather annoying, but as you will see in a minute, it will turn out to be all right. Sine A. Fine. So here is the devilish trick. Here's the devilish trick. You see, you remember that, in fact, this R2 squared is R2 squared cos squared B plus R2 squared sine squared B. Are you with me, çocuklar? Cos squared, sine squared makes up 1. That's all. It's just and R3 squared is R3 squared cos squared B plus, cos squared C. In fact, the opposite. I will take C here, and I will take B here. Okay. So what's all this? What's all this theater? Well, here we are. Now that's really unexpected piece. You know, manipulations are. People find manipulations despicable. Well, I don't. You know, they can be very clever. Look at this now. So I can now write R1 is equal to, well, I've got R2 sine C squared, R2, R3 sine B sine C, and I've got R3 sine B squared. So I can in fact write this, R2 sine C plus R3 sine B squared. This, hanımlar beyler, gives me this object, and this object all together. And then I can also write R2. Yeah, as you can see, I consult my notes all the time. I don't want to make a stupid mistake. Cosine B squared. Do you observe? That gets me R2 squared cosine squared C, R3 squared cosine squared B, minus 2R2 R3 cosine B cosine C. Exactly. That's wonderful. And the whole thing is, of course, within the square root sign. And downstairs, still, my sine A is awaiting to be woken up into action. Hanımlar beyler. Of course, this is a positive quantity, this is a positive quantity. So if I strike this out, I will obtain something smaller. If I consider this to be 0, then I've got something smaller. So, and this is square root, so I've got this R2 sine C plus R3 sine B divided by sine A. And let's remember, in order for this actually to be an equality, this must be 0. Remember that. Remember that by all. Pekala. Şimdi çocuklar, I can, the very first day I told you, make use of good cyclically arranged notation so that you don't have to repeat the computations. Now I can do the same thing with R2, and what do I obtain? 1, 2, 3, 1, 2, 3. It's counterclockwise fashion. I shall ABC, 1, 2, 3. R2 is replaced by R3, sine C is replaced by sine A, plus R3 is replaced by R1, sine B is replaced by sine C, sine A is replaced by sine B. Finally, R3 is larger than, R3 is replaced by R1, sine A is replaced by sine B, and R1 is replaced by R2, sine C is replaced by sine A, and in the denominator we have sine C, and let's put them all together. And That's the result is really rather remarkable. So let me put them together. R1 plus R2 plus R3. That is larger than. Now, I have to be careful. Let me fix let me fix R1. R1 is given with coefficient sine B over sine C and sine C over sine B. Here I am. R1 within brackets sine B sine C plus sine C sine B. Hanımlar beyler, I invite R2. How about R2? R2 has got sine C over sine A and sine A over sine C. Do you remember my first? Before I started, I wanted to say something about the arithmetic mean and the geometric mean. Do you remember? X over y plus y over x is always larger than 2. That's wonderful. That is truly okay. Sine A, sine B. As you can see, I can close my eyes and just write down the equations because I've chosen my notation in cyclic fashion. Each one of these things is larger than 2. Larger than 2. Larger than 2. 2 R1 plus R2 plus R3. It's done. It's done. Not only that, you can also ask the following question. When does this thing reduce to an equality? Well, in order for this to reduce to inequality, each one of these things must be 2. Well, x over y plus y over x. If it's larger than 2, if it is 2, then x is equal to y. So if each one of these things turn out to be exactly 2, then sine A must be equal to sine B, must be equal to sine C. So your triangle, in fact, must be an equilateral triangle. Not only that, you see, there is also this step. In each step, in order for this to be an inequality, you must have this. You must have R2 divided by R3 must be cos B, cos C. And you must have R1, R2 equals to cos A. So you see, so all of them must be proportional to the cosines, and there is only one way of doing it. The point P must stand at the very center of that equilateral triangle. That's the only way. Okay? So that's the Erdős-Mordell inequality, and this is how you can attack it by the two lowly, humble, okay, so stupid and archaic rules, the sine rule and the cosine rule. Okay, I think this is a good place to stop.